Hello, Dr. Leung.
Hi there. I'm just going to try the screen sharing and make sure everything looks okay.
Sounds good.
Can you see?
Yeah, it looks great.
The slides now. There we go. Okay, I can see. Yeah, I put on a secondary screen so that I can see both the conference website and then also my screen. So
Amazing.
this would work out.
Okay, hi guys.
Hi, Maya.
Really quick, Cecilia, how do I pronounce your last name?
Leung.
Leung.
Yes.
Okay, perfect.
And do you want me to leave my screen off for now until you introduce me and then I put everything on? How do you want to do this?
Yeah, sure, that works. Can you actually share your screen so it's like working how you can click it yourself?
Mm-hmm.
Okay, that's good.
Do you want me to project that now?
It's all good. I think she's got it. She even has a secondary screen, Maya, so she can see both.
Oh my gosh, that's great.
You're one of the most set up people so far, Dr. Leung, so you're doing great.
Well, Maya really helped me on Wednesday, I think, try to figure this out in the dry run.
Yeah, I think we were all just trying to figure it out. So, no, yeah, that was good actually, because not many people came to the dry run.
All right, people should be coming in. We have 6 people so far.
Great. How has the rest of the sessions been going? I've been like popping in and out when able.
It's been really great. We've had some amazing speakers, and I had a great time right now. I was in the expo booth talking to other students, like with their teams, what they're doing. It was awesome. It's been really gratifying to see everyone enjoying it.
That's great. Yeah, I know most conferences are online now, so like there's some limitation on that front, but I think you guys are doing a great job.
Oh, thank you.
Thank you.
How does the chat work? Are folks popping questions in there? Should I be monitoring that on top of advancing slides and so on? Or do you want to keep things at the end? I'm fine either way. It's not that big of a deal to me.
Whatever you prefer, we can go through your presentation and take Q&A at the end, or we can do it throughout, whatever is best for you.
Yeah. How about I go through if there's like something urgent that somebody wants, they can pop in the chat. If I see it, I may address it. If I don't, then we'll loop back to it at the end.
And then we'll do Q&A, and I can keep tabs. I'll try and like track questions, and it'll all be good.
Yeah.
All right.
Okay, so you think we're good to go?
Yeah, I think you're good to go. Go for it.
Okay. Hello, everyone. I am Maya, and welcome to the second speaker series of the Ascension. Our speaker for this session, Dr. Cecilia Leung, will be talking about Mars technology for the atmospheric entry and sample return. Dr. Cecilia is a planetary scientist specializing in the present-day water cycle on Mars. Her research focuses on the atmospheric structure and dynamics of water, dust, and winds in the planetary boundary layer and in the lower atmosphere. Cecilia is currently working at NASA as a NASA postdoctoral program fellow at the JPL, working to understand the vertical distribution of water vapor above the landing sites for the Phoenix Mars lander and the Curiosity rover. With that being said, I will now hand over the attention to Dr. Cecilia as she discusses this fascinating technology on Mars.
Well, thank you so much. It's a pleasure to have you join me today as I go through some of the Mars technology that we use to enter into the atmosphere of Mars, as well as some of the new upcoming developments that's going to be enabled for sample return. So I'm going to start this presentation off with something that was near and dear to my heart in 2021 in February, and that was at the time of the Perseverance landing. So I'm just going to show this little clip and remind us of what an exciting time that was.
Parachute deployed. The navigation has confirmed that the parachute has deployed and we're seeing significant deceleration. Extracting maneuver has started. About 20 meters off the surface. We're getting signals from MRO. Touchdown confirmed. Perseverance safely on the surface of Mars. Ready to begin taking the stand of past life. Looks like we're getting the first image.
This is the most amazing thing. This is what NASA does. This is what we can do as a country.
All right. So are you able to see my screen again? So what happened was there at the time we were looking at the images of the folks that was in mission control. Given the pandemic, a number of us was able to go on lab, but then also a number of team members were watching the entry, descent, and landing from their home, just like everybody else around the world as well. And it was such an exciting time to see that first image from Perseverance come down. And so in this particular mission, there were 25 different cameras. And this was one of this image from the hazard camera was just released seconds after landing. Given the distance between Mars and the Earth, there's an 8-minute delay between when the signal was received, when things happen, and when the communication signals is arriving on Earth. And so we were just hanging tight, waiting for that first confirmation of successful landing, and then, of course, seconds afterwards, received this image, and everybody celebrated. It was a great time. And then so on top of that, just a few under 24 hours, we got our first high resolution images that came down from the color imager, and then also from the descent camera, looking at how the sky crane was lowering Perseverance down onto the surface. And so because we have a number of spacecraft on Mars right now, we have also cameras that are able to capture the descent from orbit. And so here we have the high-rise camera taking an oblique image of Perseverance as it was coming down on its parachute. And so we really do have a fleet of assets around Mars right now that's able to capture all of these amazing images in real time as a landing is occurring. And so as in the introduction, I'm currently a postdoctoral fellow at the Jet Propulsion Lab. And here I'm pictured on lab, and also being able to look at the spacecraft assembly facility where Perseverance was assembled. So prior to arriving at JPL, I did my PhD in the Lunar and Planetary Laboratory at the University of Arizona. But really, I'm a Canadian at heart as well. I was born and I was raised in Vancouver, British Columbia, and I did my undergraduate degree in York University, where I did a physics and astronomy degree. And only at that time, they had a space communication major, and that was really exciting. So I'm very familiar with SEDS and SEDS-Canada, and during my college days, I really enjoyed participating in their events, and it's just really fun to come full circle. And those times when I participated in SEDS really inspired me to the career path I went down today. And so I'm currently loving my time at JPL, and then all of the opportunities that it's providing me, especially in terms of the Mars sciences that I've been able to perform. And so Perseverance is one part of a much larger program, the Mars Exploration Program. And so I'm sure you've heard of other rovers, landers, and orbiters. And so this is a part of a multi-decade strategy. I'm looking at one overlying defining question for Mars exploration, and that's looking at whether there could have been or could be life on Mars. And so amongst all of our discoveries, this one stands out because is there a possibility that the presence of liquid water, either in the past or could have preserved subsurface life on Mars today, and whether the environment could have been habitable for life? And so there are 4 main goals of the Mars Exploration Program to determine if life arose, to characterize its environment and climate, geology, all in preparation for future human exploration of Mars as well. And so some of the landers and rovers I was mentioning earlier might be familiar to you. The Mars 2020 rover, now called Perseverance, is down on the right-hand side, along with the InSight lander, Curiosity rover, and Opportunity, and those were all landed assets, and they're all also accompanied by a number of orbital assets as well. So this particular graphic looks at the number of missions that NASA participates in. There are also a number of missions that's run by other international partners, such as India, China, the Emirates, that are not currently on this figure, but they're also contributing to our overall goal of Mars exploration as well. And so previously we had a strategy of following the water, and it's evolving into exploring habitability and looking for signs of life as well as human exploration. So then, I'm just going to take a little step back and look at where have we gone in the past. How did we get here, and what are the lessons we learned along the way? And so the Mars Exploration Program had a long history, and then one of the first flyby of Mars occurred in 1964 with the Mariner 4 probe, and that's the left-hand on the left-hand upper corner there. And so there's a period of time when we had all the Mariner probes, Viking, orbiters, and lander, and a long hiatus until the 1990s, where we had the Mars Global Surveyor, Mars Pathfinder, and then into the 2000s, we finally had a nice suite of missions that was almost one after the other until present day. And that's a really exciting time. That's why we have had a really great wealth of information and data coming back from the planet Mars. And along the way too, we've really increased our development of ways to land on the planet. And so looking at this suite of spacecraft then, starting with Mariner, I was telling you a little bit earlier how quickly the first image of Perseverance came down. It was within seconds, and we were able to see the surface of the planet. That wasn't the way things were back in the 60s. I love this little story just to highlight how far we've come. So in the 1960s, Mariner 4 performed the first flyby of Mars and returned the first close-up image of Mars. And so at that time, there were digital imaging processors on board that was able to translate into the numbers how each of the data based on how bright each pixel was. However, those computers took a long time to process images back in the day. And of course, transmitting all of that data back to Earth took a long time as well. And so while all of the scientists and engineers waited at that time, they actually figured out a way to preview this image data based on coloring in the number of bits. And so this image shows a telecom engineer printing out the strips of ticker tapes, and each of the tape had the number associated with how bright that particular that pixel was. And then using a palette of oranges, yellows, and browns, they colored in what they would have seen had the image been processed and returned to Earth. And so this was like the first image of Mars that we saw was using this method, similar to what we use as paint by numbers today. So that's just an interesting, fun fact. And so what ended up happening after we compressed the colorized image, so now we're looking at side by side the color ticker tape colored image versus the real image that eventually came down. And the brightness was showing of the cloud cover on Mars. You can see the orange shows the limb, and then the dark brown showed the dark sky. And I just love this because no matter how many missions we've sent to Mars, to other planets, we just can't wait to get this data back. And we're just always sitting at the edge of our seat, just incredibly, very childlike, waiting for this image to come down so we can analyze it and see what we can learn about it. And so coming back to a little bit for the present day, I was mentioning there's this suite of orbiters, landers, and rovers. And so how does it fit into the overall planetary exploration strategy then? You'll see that the first one, like I said, Mariner 4 was first a flyby mission. And typically, we send a flyby mission to do a very quick reconnaissance of the planet, after which we can send an orbiter. And so an example of that is the Mars Reconnaissance Orbiter that's currently still in operation today, bringing a lot of high-resolution images as well as spectroscopic data about the surface composition, etc. After we orbit the planet, then we have better information about where is a good place on the planet to land. And so an example of that, first we sent the Viking landers, but later on there was also the Pathfinder lander, and then later we have the Phoenix lander, Insight lander, etc. And so finally, after we've landed on the planet, we could also consider send, if it's the planet, such as Mars, we send rover so that we can, instead of one stationary location, then we can send this robot in order to roam around this landing location and see what kind of data and samples we could collect. So looking at so now the sequence is an initial observation, reconnaissance, as well as intensive study of the locations. All right, so in terms of landed spacecraft, these are the landers and rovers. Where have we landed? And so this particular image looks at all of the locations that we have landed so far. And then adding to this, from this year, we have the Perseverance lander. We also have a Chinese mission called the Tianwen-1. And later on in September, we're hoping for a successful launch and subsequent landing of the ESA's Rosalind Franklin rover as well. And then so this would comprise of all of the landing sites that we would have place spacecraft on Mars. And so part of this presentation is look at what do we do? What do we need to do in order to successfully put spacecraft onto the surface from orbit? And so this image shows a typical descent sequence. Some of the earlier Mars landers, such as the Vikings and the Soviets lander, they first rode along on an orbiter, and from orbit it was released, and then a parachute would bring the smaller sized rover at that time down to the surface with some thruster. And so typically now we either have a ride along on orbit, or we send a lander or a rover as a standalone as it enters into the upper atmosphere. And we call that sequence the entry, descent, and landing. And so we have at 21 kilometers or 21,000 kilometers per hour, up at an altitude of 120 kilometers, that's when the spacecraft initially enters the atmosphere. Mars's atmosphere is very thin compared to that of the Earth. It's less than 1% of the density of the Earth. And so there really isn't that much mass to slow down the spacecraft. And so as you're hurtling through the thin atmosphere, there really needs to have, we have to be innovative in terms of how can we slow down the spacecraft enough so that it could land softly onto the surface and for the spacecraft to continue its operation. And so typically we have a heat shield and then a back shell and a parachute that brings it almost to the bulk of the lower atmosphere. At that point, you have thrusters or retro rockets, and then a number of innovations at that point to touch down. And so that worked well for a time. And then, so as rovers and landers got heavier and heavier, we need to figure out new methods in order to slow down increasingly heavier spacecraft. And so I'm going to talk about a few of those in the following slides. So first of all, we have with the Mars Exploration Rover, and that's the Spirit and Opportunity rovers in 2004, they used these airbags. I think they're hilarious looking back at them, but it really worked at the time. And this was not the first time that this method was used. It was successful during the Pathfinder days, and then so it was once again used for Spirit and Opportunity. And so at that time, what happened was we go through the typical sequence with the parachute and back shells and retro rockets firing. And so, but afterwards, near the last 3 kilometers or so of the atmosphere, these airbags would inflate. And then so in doing so, the inflated airbags housing Spirit and Opportunity inside would cushion the landing of the spacecraft onto the surface. And as you can see on the right, this massive airbags are just bouncing onto the surface of Mars until it comes to a stop. At that point, the airbags are then cut off from its back shell and then it bounces until it stops. It unfolds and revealing the rover inside. And so that was interesting. And so for 2009, the Phoenix lander was a smaller platform, and some of the previous technology had worked. But in 2012 then, the Mars Science Lab, or the Curiosity rover, once again, now we're upgrading the mass of this rover to a 1-ton vehicle. Never before have we sent something this heavy to Mars. And so with a much larger vehicle, a heavier vehicle, a lot more is now at stake in terms of being able to land that safely. And so one of the maneuvers engineers at GPL and others came up with was this sky crane. And so on the lower left, you can see the vertical extent of the sky crane with its with the descent stage, as well as cables that was going to lower the rover down. At the same time, on the descent stage, there were going to be 4 rockets that retrofires to slow it down as much as possible, so that Curiosity could land safely. And on the right-hand side, on the upper right, you can see how that was an artist's concept of how that maneuver took place. You can see again these cables lowering down the rover while the sky crane kept it from coming down too quickly with the retro rockets firing upwards. And so at that time, this was really innovative. We had never seen anything like that before. And prior to landing, it was quite nerve-wracking in terms of like, is this really going to work? But you know, in hindsight, it worked. It worked perfectly, and it was just so, yeah, it was amazing to be able to witness that landing at the time. And this heritage now is being used in Perseverance and later technologies and later spacecraft as well. And so moving on to the InSight lander. So for the InSight lander, it wasn't so much that the spacecraft itself was heavier than the previous, or that they needed a new way to do entry, descent, and landing. The interesting about this particular landing, and it was the season at which it was landing. And so Mars has all of these periodic dusty season based on its ellipticity as well as its how close it is to the sun. And so consistently during this time of year, then you're going to get a dusty season. So right, there we go. And so what we needed to do in advance of the landing was model all of these scenarios. And so I was participating in part of this work in terms of what kind of dust scenarios could the spacecraft encounter, and would that fall within the engineering constraints? And so we had smaller regional dust storms, much bigger global dust storms, or just nominal dust. And so we had to at least model all of these behaviors so that we could make sure that the onboard software as well as the engineering constraint could handle these conditions. And so moving to the most recent rover now, coming to the Perseverance rover in 2020, like we were saying like we saw in the video at the very beginning of the presentation. Once again, after the parachute and retro rocket firing, it also used the SkyTrain maneuver. However, on top of that, what's new for the Perseverance landing was there's a system called terrain relative navigation. And what this did, how this worked, was the spacecraft would take images during the parachute descent and then match them to onboard high-resolution maps. And so it's able to use the position of the solution to list out the number of safe landing locations and then thus selecting a landing target. And so this was important because it's in this way it could onboard autonomously avoid hazards. And so for Perseverance, that was really an Easter egg was on the parachute coming down. It actually had a secret message. It coded to the parachute's color coded to a message called "Dare Mighty Things," as well as the GPS coordinates of JPL. And of course, on board Perseverance was a ride-along mission called the Ingenuity helicopter, and this was a technology demo, and it demonstrated the first controlled flight on another planet, and its ability to use this new aerial mobility to explore future landing locations. So both of these are ongoing right now, and we're really excited of what Perseverance is going to be able to teach us about, further teach us about Mars. And so the story of all of why I was showing you all these different landing systems is that all of these are improving the accuracy of how we can land on Mars. And so previously, back in the Viking days, we had this really large landing ellipse. And so what each of the newer technology is essentially doing is shrinking this ellipse smaller and smaller, such that with each improvement, the landing system is able to shrink the region of confidence that the onboard autonomous system could land within. And so the smaller you make the landing ellipse, the better you'll be able to constrain the region of interest. And in the future, we might be able to land more confidently in places such as canyon systems or close to cliff edge that currently would be too hazardous to land. And so I'm going to switch gear a little bit here and talk about what is next for Mars exploration then. And so we had talked about the Perseverance rover, and it so happens that Curiosity rover fits within that Mars exploration program strategy in a very significant way. In fact, we have a document called the Decadal Survey that planetary scientists use to identify what is the highest priority missions that we'll be sending to the planets, different planets in the following decade. And the one that was the Decadal Survey that was conducted between 2013 and 2022 had identified Mars sample return to be of the highest priority flagship mission that planetary scientists should send. And so we are on, we have completed the first step in this sequence of multi-mission sample return strategy by sending the CASH rover to Mars. And what's coming up next then is we have all these samples on Mars. We're going to try to bring them back with a number of different new rovers and new rockets that's going to enable bring all these really interesting samples back to for analysis on Earth. Oops. And so what's going to need is that first, right now we have the sample caching rover, and that's the Perseverance rover. Next then is a series of 3 elements, and that's going to be contained in the mission called the sample retrieval lander. And that's going to both include a fetch rover. That fetch rover's job is to pick up the samples that Perseverance had located and then bring them back to the sample retrieval sample retrieval lander, after which there's going to be a Mars Ascend vehicle, so a rocket that's going to send the sample that's collected by the Fetch rover from the surface of Mars up until an orbit that's a spacecraft that's waiting in orbit. And so the third phase is now this capture and containment system on board of an Earth return orbiter that's going to retrieve the sample that's being shot up from the rocket. And from the final phase of all of this is this orbiter is going to come back to Earth and eventually enter the Earth system so that the samples could be safely returned and analyzed. And so that's sort of summarized in this graphic in terms of first step, we collect the samples and deposit them into collection tubes. Number two, we use a Fetch rovers to pick them up and transport them to the lander with the small rockets that's going to blast this canister up until an orbiting spacecraft that's waiting to collect this sample. And then the orbiter, once again, is going to leave Mars and return back to Earth. And so we're already well on the way of the first step. As of the end of 2021, so just a few weeks ago, Perseverance has already collected 6 samples. And so Perseverance initially landed in Jezero, near Jezero crater, and is following this white traverse and collecting samples along the way. And it has already collected 6 samples. Within its prime mission, it has a goal of collecting 20 samples. And on board, it has the ability to collect 43 samples in total. And so then the $1 million question is, we need to bring these back. And once again, I think the best way, I went through the sequence briefly, but the best way is really to watch this wonderfully animation showing what's going to actually happen.
The rover has placed its collected samples on the Martian surface. A second follow-on mission would land nearby, deploy a small rover to fetch the samples, and bring them back to the lander, where they would be loaded into a container and placed atop a small rocket. The rocket would then lift off, carrying the samples up into Mars orbit. Waiting in orbit would be a third spacecraft, an Earth return orbiter, that would find the samples in space, catch up with them, capture the container, and bring it back to Earth. With Mars samples safely back on Earth, scientists around the world would be able to study them in state-of-the-art laboratories for decades to come. The payoff of a sample return would be a breakthrough in our understanding of the history of Mars and of the potential for life beyond our home planet. After the Mars...
Awesome. And so I'm just going to leave this final slide here and just comment that that whole sequence does not look easy at all. There's going to be a lot of testing to make sure that technology are going to be tested so that we will be able to successfully perform these maneuvers. And so even though it looks really challenging, it's something that really excites us who are currently working to enable the sample to be brought back. And so when we were doing, when we were looking at the sky crane maneuver for the Curiosity and Perseverance, that didn't look easy either. And that sequence was dubbed as the 7 minutes of terror. So similarly, I think that there's no coincidence that on the parachute of Perseverance is labeled Dare Mighty Things. And that's a strong slogan here at JPL. And that's driving innovation in formulation, new mission concepts so that we can enable more and mightier things as we continue our journey in space exploration. And so in that spirit, we're gonna grab hold of these opportunities to make the most of these opportunities where previously deemed impossible, we're gonna make them possible. And so thank you so much for joining me today and on this whirlwind tour of past and present and future of Mars exploration. If you're on Twitter, I'd love to connect with you there. My handle is Celestial Says. And I just want to thank the organizers of Ascension 2022. It's been a wonderful conference so far, and I really look forward to, and look forward to the rest of the programming and hope you enjoy it as well. So thank you very much.
Oh, thank you so much, Dr. Cecilia Leung. It's been amazing. It's great to hear about these incredible missions you're working on. I'm going to pull some questions from the chat, if that's good for you.
That's
and
wonderful.
Also, I might throw in a couple of my own. So if anyone has questions, please put them in the chat. The first one from the chat is MSL spectroscopic data available online? Do you happen to know that?
Yeah, and so if you go on something called the Planetary Data System, given that these are all publicly funded missions, all of the data is publicly available as well. And so the NASA Planetary Data System will have all of, not just MSL data, all of the data that's been collected with the previous samples. And so there is a proprietary period of a few months where only the team members can look at the data, but anything after that period gets uploaded online, and literally anyone can download that information for use in analysis themselves.
That's amazing. And then I had a question for me. I know that you're an expert in Martian atmosphere and the Martian water cycle. What does a typical day look like? How do you contribute at NASA JPL? What are you involved in?
So I love being a scientist because like every day looks different. I think as with everybody else on lab, we have our hands full with multiple projects all at once. And so my primary research is on the Martian atmosphere. And so I spent a lot of time looking at my computer modeling as well as looking at spacecraft data. And so I was mentioning the Planetary Data System. I go on there myself and grab the necessary data I need to use for the project I need. Of course, I need to define what that hypothesis is with my team priority to see what data sets I want to query, because there's just so much data out there available for use. And you can easily be overwhelmed. And so I use data that's both from orbiting spacecraft, in particular that such as temperature and water ice, as well as dust profiles that comes down from the Mars Reconnaissance Orbiter or the Trace Gas Orbiter, that's an ESA mission. And so I combine that with some of the data that's coming down from the landers and rovers. And so something that I like to do is looking at different data sets simultaneously. And so what's really wonderful about having this big suite of spacecraft is that sometimes you're able to gather information both from orbit as well as from the lander at the same time. And from orbit, you have this wonderful way to look all the way down to through the profile of the atmosphere, that maybe it's not going to give you the highest resolution right at the surface, versus your surface lander or rover is going to have this really high resolution image or composition data that you want to use. And so in combination, it's really this wonderful opportunity to be able to use multiple spacecraft data all at the same time. And so that's more on the research side. I either use analytical techniques or computer modeling to do statistical analysis or modeling different phenomena like that. I also look at, we have ways to look at future missions as well. And so there's some things called mission formulation office, where we're literally, if there's the opportunity arise, sometimes we're gonna bring together a number of experts to say, okay, in the future, if we could dream up a scenario where we could bring down a mission where you can climb down the edge of Valles Marineris. What kind of science would you do and how would you do it? Or in the future, we can fly a much bigger helicopter than the Ingenuity helicopter. Where would we go? And what kind of science is the most going to be the highest priorities? And so some of my work and working with others on lab is to think about these future concepts and some of the providing some of the guiding science behind why we would want to go where we want to go and what are the science hypotheses that we want to test.
Wow, that sounds really exciting to explore Mars in that way. We have some questions in the audience about how to get involved as a Canadian student. Are there any opportunities, undergrad, grad, or PhD level Canadian students to get involved?
Yeah, there's so many. Even at JPL itself, there's a student internship program. And then I think so this is for JPL as only, it's not for JPL only. JPL is only one of the NASA centers. There are internships across many of the NASA centers, including Goddard Space Flight Center or Johnson Space Center, Kennedy Space Center. And you just have to just Google NASA internship for students, for example, and then you should be able to pull up a page. And that happens mostly in the summertime. You can have internships where in the science divisions, you would pair up with a scientist such as myself or one of my colleagues, and we define a small project where you could complete that in 12 weeks. And some interns do these for multiple semesters. And so you have the opportunities, if you really enjoy a particular project, to continue to do so. Or if you're a grad student and you want to publish one of your papers using data and be a part of lab for a period of time, there are also opportunities to do so as well. And that's they will ask you for their citizenship. And so I think there's some that that may have citizenship restrictions, especially if you're an engineer and wants to work on technology side of things. But as a scientist, many of them are open to many nationalities, as the data I work with on a daily basis is open for all.
Oh, that's amazing. Now we have a question from Harsh. What would you recommend for a person who is a novice at studying the Martian atmosphere? And where should I start? I'm a geologist with some general background and understanding of atmospheric science. I'd appreciate your advice.
Yeah, oh, that's a wonderful question. So you definitely do not need to be an atmospheric scientist to study planetary science or the Martian atmosphere, or there's just so many aspects of planetary sciences that takes into account all different backgrounds. I had my initial education was in the physics and astronomy stream, and so when I was an undergrad, I think I was interested in a variety of different topics, including nuclear physics. And I was an observer for a long time before switching to planetary science in general. And the thing about planetary science, it employs so many different skills, including geology, including atmospheric science, including astronomers, including engineering principles and data scientists and machine learning. And really, geology is actually one of the more common disciplines that planetary scientists have backgrounds in, because a lot of the world will be looking at the surface of these planets. And so in terms of where to start, if you are if you are doing research yourself already, speak to other scientists who you might want to collaborate with, and then that's one way to get onto a project or be able to write a proposal together. Or if you're a student, definitely look into those internship opportunities. And it's not and intern mentors are definitely not looking for specific interns that have specific skill sets. Part of this internship program is to provide an experience where earlier career folks can have the opportunity to try different subdisciplines and to see where they really excel in or really like, so that they can pursue their graduate or the rest of the career in various different disciplines. And so the internship program is a great way to try out something new, even if you don't necessarily have the specific background in it.
There's a good question here that's along the lines of our theme of the conference, innovation and technology. They're asking, are there any new technologies that you can foresee that will make the job of bringing the samples back easier than getting a whole rover there, collecting samples, and then having a return mission?
Yeah. And so part of why it's split up into so many pieces, unfortunately, is there's a cost limitation. If we were given multiple billions of dollars, we could streamline this process a little bit more. But due to there is a budget that Congress has to approve for NASA to operate every single year, it's going to be more feasible to do this piecewise. And so Perseverance itself is already $a billion, and this whole entire sample return architecture may be maybe $10 billion. And so all at once, you're just not going to have the budget for it. And so instead, for each, every few years, we prioritize sample return and do one piece of the architecture so that we can leave some of the budget for outer planets as well. I know some of the planetary scientists always say Mars gets so many missions. We do in terms of spacecraft wise. But again, like we need to do something like sample return. It's such a large endeavor. And so we're trying to do that in piecewise. I think I would also love to bring orbiters and sample return missions to ocean worlds as well. And so there is a juggling in terms of how you're going to split that budget most efficiently to do all the really cool things that we all want to do.
Maya, did you have a question you wanted to ask?
Yes, I just put it in the chat. More of a fun or random question, you could say, is would you ever consider a one-way trip to Mars?
So there are opportunities. There had been opportunities like that out there. I personally did not apply to those. I think it's admirable that other people will have those opportunities. I enjoy being a scientist. I enjoy interacting with folks socially. And so Earth is a beautiful place. And if you really consider what it means to be stuck in a journey in a tin can to arrive to Mars, like that's very confined quarters already. But that's not to say that it's not going to happen in some of your lifetimes. I think we will be able to send humans to Mars in the next few decades. And so some of you might have the opportunity to do so. I just personally would not be the one volunteering for a one-way mission.
I can relate. Some people really want to be an astronaut, and I want to build the technology that goes to space. I like it here on Earth. So
the creature habits of like a soft bed, for example.
Or a bath. Oh, it's nice. Thank you so much for coming, Dr. Leung. It's been such a pleasure to hear about your work. It's so inspiring and amazing to see a fellow Canadian doing so well at NASA JPL and see all of the interesting work that you get to be a part of.
Oh, you're very welcome. It's a pleasure to speak with you as well. And I love speaking with students and see what kind of fresh new ideas that they have in terms of the upcoming decades as well, because like your ideas may be really impacting what we do next in the next few decades.
Everybody, if you want to head over to the main stage, the next session will be highlighting student research. We have our SEDS-Canada projects, including the Reduced Gravity Experiment, the Stratospheric Balloon Challenge, and the Arctic Research Expedition. So you can hear more about how to get involved in these research projects, as well as hear about the research that's already been done by student teams. So I hope to see you over there at the stage. Thank you, Dr. Leung.
Yeah, thank you. Thank you all for coming.
Bye.
Thanks all.